Okay, we're going to be doing forms of logical statements here. This is actually video 4. That was a typo. And this is very important for the rest of the work in this class. We're actually going to be using the stuff we do today in this video repeatedly, especially when we come to proofs. Okay, so in the last video, we talked about a conditional statement, right? We have a conditional statement which looks like P implies Q, as read as P implies Q. And we know that it is false if and only if its hypothesis P is true and its conclusion Q is false. So I'm looking, we can put this truth table back together. If I offer you a job and I give you the job, I'm telling the truth. If I offer you a job and I don't give you a job, then I am telling a lie. If I don't offer you a job, then I could either give you a job or not, and either way I will be telling the truth. And again, recall these last two rows are known as vacuously true. So, given this truth table for an implication, what's the negation of that implication going to be? Well, we have our truth table. We can just take the negation, which is the opposite. So where our implication is true, our negation is going to be false. Where our original statement is false, this is going to be true. And then false and false. Right, so what does that mean? It means that the negation is true, right here, this negation is true if and only if P is true and Q is false. That is the only time we get a truth here, right? This is false, this is false, this is false. So one way of writing the negation of P implies Q is to look at, with this negation, what makes that negation true? Well, the only thing that makes it true is this scenario. So this is when P is true and Q is false. Okay, so if there were multiple rows in this truth table that were true, then this would be more complicated. But given that there's only one row that's true, what I can do is I can specify the details of that row. Well, P is true and Q is false. Well, how do I indicate that Q is false? Well, I say that the negation of Q is true. Right? So this is the negation of an implication. Okay. Oh, well, yes. So this is P and not Q, as we did before. Okay, so given that, and here's our truth table of everything, how are we going to be able to write P implies Q without using an implication, which is the little arrow? Well, P implies Q, so now we can ignore this column a little bit, and let's do some algebra here. So I'm going to say P implies Q, and we know that this column is the opposite of this column. So I can say is equal to the negation, or the opposite of the negation. And that should be clear from the double negative law. Let's see if I can write that in here, by the double negative law. But looking back at this statement right here, what can I do with it? Well, I see there's this extra negation sign that we can suck into the group via I'm sorry. Excuse me. I'm skipping steps. We saw last time that this statement right here, we know what that is, right? That's right, given right here. So what I can do is I can replace it, and I can say equivalent, that this is equivalent to that statement is negative P and not Q, because I'm just substituting this value in for that. Okay, and so this is by substitution. And what do we know looking at that statement? Well, I see that negative sign outside of a group. So I can use De Morgan's law to suck that line, or suck that negation inside. Remember, with De Morgan's law, we flip the operator, and then this becomes negation of Q, and this is by De Morgan's. Well, and now I can use the double negative law on this. So I get that this is not P or Q by the double negative law. So it's a little confusing down here. I'm going to rewrite it at the top. I'm going to say that P implies Q is equivalent to not P or Q. And if we take a look at our truth table, not P is one of these last two rows. Okay, I'm just confusing myself there. Yeah, the algebra all works out. So what we have is we have an equivalence between an implication and a way of writing that implication without using an arrow, with just using or and not. So not P or Q. Okay, so this is going to be really important. And I'll tell you honestly, I can never remember it. Every time I need to know that, I always go through this math right here. I just scribble it out because I know that P implies Q is equal to the negative of itself. And then I can remember the negative, because again, knowing the negative is going to be important as well. So knowing that P implies Q is equal to not P or Q is important, and so is knowing the negative of P implies Q is equal to P and not Q. So I'm very opposed in general to memorizing things, but you really need to memorize at least one of these, because from one of them you can get the other. So these are both very important. Okay, some more definitions you need to memorize. Remember, we know that there's two ways of writing an implication. We can write it with an arrow, or we can write it with a negative sign and an or. These are just definitions. So I'm going to define the contrapositive to be equal to the negative of Q implying the negative of P. So remember, our normal implication is P implies Q, and now the contrapositive is negative Q implies negative P. So let's do a quick truth table of this and see what happens. There's not a lot of room here. I'm just going to kind of overwrite this. So we're going to have P, Q, not P, not Q. P implies Q. And then finally, not Q implies not P. Okay, so my usual now I take the opposite of P, which is of course this column. So that's going to be false, false, true, true. And then take the negation of Q, which is false, true, false, true. Now, P implies Q, looking at these two columns, and this is true, false, true, true. And now not P implies not Q, or not Q implies not P. I'm looking at these two columns, but in reverse. So I did a poor job of writing it out, but so does false imply false? Yes, that's actually vacuously true. Does true imply false? No. That is the one time this is not true. False implies true, yes, and true implies true. True. Hey, look at something. These are the same, right? So both the truth tables for P implies Q and not Q implies not P are identical, which means that this contrapositive is another way of writing an implication. They are equivalent. Which means this is equivalent to the implication. Okay. The next one you need to memorize is the converse. Now, notice here, this is P implies Q. Here we swap them around. Q implies P. So again, if we're going to do a truth table, let's do a quick one. P, Q, P implies Q, and Q implies P. Got true, true, false, false, true, false, true, false. P implies Q, we know is true, false, true, true. Now Q implies P, so we're doing it the other way around. Does true imply true? Yes. Does false imply true? Yes, that's vacuously true. Does true imply false? No. Does false imply false? Yes. But now take a look. These columns are different. In particular, they're different on these two middle rows. So the converse is not equivalent to our original statement. Okay. So this is not equivalent to the state implication, the original implication. Okay. The inverse is similar. I'm sort of giving something away here by saying that the converse is equivalent to the inverse. And indeed, the inverse is equivalent to the converse. But I'm going to leave that up to you to do the truth table for that. The inverse is we take the P implies Q and we do it in the same order, but we negate them. So now it's negated P implies negated Q, and this is not equivalent to the original, but it is equivalent to the converse. And very finally, we have a negation. We already saw that the negation is P and not Q, and this is the negation of the original. So it's the negation of the original, and it is not equivalent to anything, in fact. And again, I'm going to leave that up to you to do the truth table to verify that. But the fact that the contrapositive is equivalent to the original is very important in the future. Okay. Let's plug this in. So let's do some examples of this. Here's my statement. If you paid full price, so this is P, and of course these can be any variables. It's just traditional in logic to use P and Q. Then you didn't get it at greatdeals.com will be Q. This sounds like an advertisement you probably see all over the place. So let's look at the contrapositive. Remember, right now we have P implies Q, and the contrapositive is not Q implies not P. So Q is the second part. You didn't get it on greatdeals.com. So I'm going to take the opposite of that, which is if you got it at greatdeals.com, then, now notice we have to take the opposite of P. Here's P. So then you did not pay full price. Which makes sense. We know these two should be equivalent. If you paid full price, then you didn't get it at greatdeals.com is equivalent to if you got it at greatdeals.com, then you did not pay full price. So that makes sense. Let's look at another one. Same statement, but now we're looking at the converse. And again, remember this is P, and the rest of it, I'm just going to do this, is Q. So the converse, we have Q first. So if you didn't get it on greatdeals.com, then you paid full price. Right, because we just swapped the order of the two. Now, is that a true statement? Well, it kind of looks similar to this, but they're not quite the same. Just because you didn't get it at greatdeals.com doesn't mean that you necessarily paid full price. For example, what if you got it on Amazon and you got a really good discount? Or what if you got it at a garage sale and you got a really good discount? Right? Just because you didn't get it on greatdeals.com does not mean that you necessarily paid full price. So this is an example of how the converse is not equivalent to our original statement. It looks similar, but it's not the same. It's not equivalent. Similarly, with the inverse, we're going to get the negation of P, meaning if you didn't pay full price, then now we're doing the negation of this latter part, then you did get it on greatdeals.com. And once again, this is not necessarily the case. What if you got it at a garage sale? You didn't pay full price, but that does not mean that you got it at greatdeals.com. So again, this is not equivalent to our original statement. Almost done. Finally, the negation. Again, here's the negation we figured out earlier. So now notice there's no implication here. You only say if then if there's an implication. So without an implication, we don't use if then anymore. We just talk about the statements. So again, there's P, there's Q. So you paid full price and you got it at or on greatdeals.com. So this is actually the opposite of that statement, right? That's what a negation means, is we take the opposite. So the opposite of if you paid full price, then you didn't get it on greatdeals.com is going to be you paid full price and you got it at greatdeals.com. Right? And you can see how the two are different from one another. And last but not least, we have biconditional statements. All a biconditional statement is it's a statement where P implies Q and Q implies P. And so now our arrow goes both ways. All right. And this is read if and only P, if and only if Q. And a very common abbreviation in mathematics, we use this term if and only if all the time in math. It's commonly abbreviated IFF. So I'll abbreviate like it as that in the future. So if we say P if and only if Q is also the same as saying P if and only if Q. Let's do the truth table for this. If P implies Q, we have true, false, true, true. And then Q implies P, I'm going backwards. I've got true, true, false, true. And now remember, we're anding these together. This is an and. So if both of these are true, this is true. If they're not, this biconditional is false. And here they're both true, so they're true again. So what this is really saying is that as long as P and Q are the same in every particular, and I don't care if they're both true or if they're both false, as long as they're the same, our biconditional is true. If they're different, then our biconditional is false. Okay. And this is the idea behind a biconditional statement. So we're going to be doing some homework problems on this. We're going to be doing some more puzzles in class on this. And then we're going to apply all this logic, which may seem a little unusual for a math class to have gone through. We're going to see how this applies to computation, because it turns out All this logic that we've been working with is fundamental to computation. We'll see that next time.